Hi everyone, I will introduce the electrical and mechanical characterization of carbon-based elastomeric composites for printed sensors and electronics. I will introduce this project following this order: background and aim, characterization of electrical properties and mechanical properties. Then I will give an application example and several prototypes of printed sensors. Finally, conclusion and current work. Printing technology have attracted significant interest in recent years, particularly for the development of flexible and stretchable electronics, like wearable sensors and e-skin. For this new generation of devices, conductive elastomers are a popular choice. The aim of the project is to custom stretchable inks for printing and investigate and compare effects of different carbon-based fillers to meet different requirements of printed stretchable sensors. Next, characterization of electrical properties. Left side are the material used in the experiment. 4 types of carbon-based fillers: carbon black 100% compressed, carbon black 50% compressed, carbon black super P, graphite particles, PDMS, and we use the heptene as co-solvent. Right side shows the fabrication process of samples for conductivity testing. Grind the filler particles first, then solve the filler particles and PDMS into heptene. Then use stirring and ultrasonic baths to disperse the particles and the PDMS well in the heptene separately. Next, mix these two mixtures, add curing agent, and stirring again to ensure that the filler particles are well doped in PDMS. After degassing and curing, the samples for conductivity test can be obtained. Here are all the samples I have made for conductivity characterization. Is the filler concentration ranges and steps information can be seen here. This figure shows the conductivity result and fitting equations. For carbon-based material, the percolation threshold is around 10 weight% to 11 weight%. And for graphite-based ink, this value is around 25 weight% to 28 weight%. For carbon black-based inks between 10 weight% to 25 weight%, conductivity changes between 0 to around 12 Siemens per meter, while for graphite between 25 weight% to 50 weight%, this value is between 0 to around 98 Siemens per meter. The conductivity of super P-based composites is the best among the 3 carbon-based fillers, and as expected, the high compressed CB particles lead to a higher conductivity than low compression. Next, characterization of mechanical properties. The mechanical properties of 50 weight% compressed CB filler were not tested due to the significantly reduced conductivity for the same filler content compared to other materials. In this part, we did the tensile and hysteresis test using instron. The samples were made into a dog-bone shape and clamped by the instron. The wires attached on the samples were connected with an analyzer, which was used to monitor the resistance change of samples. In this part, we focus on Young's modular, gauge factor, and hysteresis of resistance. Okay, first, Young's modular. The stress strain curves can be seen on the left. The carbon black 100% compressed, carbon black super P, and graphite. And the result of Young's modular and fitting equations can be seen on the right side here. As expected, increased filler content, reduced compensate elasticity. Carbon black-based inks achieve a Young's modular between around 0.5 to 1.7 megapascal, while graphite between 0.5 to 5.3 megapascal within their respective weight ratio ranges. Next, gauge factor. Resistance change via string curves can be seen on the left. Here is the carbon black 100 compressed, carbon black super P, and graphite. The average GF values are plotted in the right figure. The arrow bars indicate the value when the average is subtracted from a minimum of GF and the maximum of GF. Samples of a low weight ratio are more sensitive to strain. The slope of curves changes very significantly. It means that the samples quickly approach a non-conductive state. Large GF value means the material and weight ratio has potential to make a good strain sensor, but may not suitable for interconnect. And the hysteresis test, using instron to stretch the samples at 60 millimeter per minute. After reaching 20% of strain, return to the initial position and repeat for 10 times. The hysteresis of resistance changes are mainly focused. As we can see in this figure, the hysteresis is obvious in the first stretch. Let me see here. And the hysteresis reduced after increasing the number of the tensile cycles. The possible reason is the conductive passes are destroyed during initial stretching, but the stretching can also cause samples to shrink perpendicular to the strain direction, so it leads to new conductive paths. Since stretching is cyclic, no more conductive paths are destroyed after the first few cycles, and the damaged ones are compensated by the new path. According to this figure, the higher filler concentration leads to more obvious hysteresis. And on the right side is the final resistance hysteresis result. At high filler concentration, carbon black super P has the smallest hysteresis. So how can we use all those results? I can give an application example here. Assuming that we need a printed resistor in a wearable device, the stencil printing will be used to fabricate this resistor, and the shape and size should be the same as this figure. And this device has a certain Young's modular and gauge factor requirement, as shown here. So how to select suitable material and filler concentration? The design solution example is here. Calculate the required conductivity based on the requirement of a resistance and the size at first, then using fitting equations to find candidate fillers and weight ratio. Next, do further filtering according to the requirement of Young's modular and gauge factor. Finally, you can find the most suitable material and weight ratio. We also printed several prototypes of sensors using mold printing, the figure A to C, and stencil printing, figure D to G. For mold printing, during mold ink deposition, ink adheres to its surface and is challenging to remove if the mold surface is not perfectly flat and if a manual process is used. This makes high-resolution printing challenging. It may cause short circuits or some unwanted features. In summary, the results and the equations allow carbon-based PDMS composites optimization for printed stretchable electronics. So the experiment is just like build a carbon-based material library for printed electronics. And AC analytes, electrochemical characterization, and semi-chemizations for silver PDMS are in progress. And we are printing epidermal sensors and robotic e-skin for biomedical application. Thanks to all contributors, thanks to EPSRC for financial support, and thank you for your attention.